Hello, and this is the lecture 4.1.2, an infinite chain of atoms, and the course is still solid-state physics. So what we will do in this lecture is that we will now couple n oscillators together, and then we will solve their subsequent equations of motions that arise. First, we will consider a one-dimensional monoatomic lattice. So we just have a single lattice in our lattice point, and we will learn what kind of dispersion relation then is related to the solution, and how it looks like in a so-called reciprocal volume of first Brillouin zone. And after that, we will generalize our treatment to diatomic lattices, and we will find out that a new solution branch emerges into the solutions and into the Brillouin zone. And let's see if we get that far in this lecture. It might be that I will need to break this into two pieces so that we will first cover the monoatomic case, and then in the upcoming part 2 we will consider the diatomic lattice. But let's see how we progress. I don't want to speak for too long per one single lecture. So now we are ready to couple the atoms together. So we already have solved a system where the atoms are not coupled, and we will now generalize this earlier treatment to the case when we actually have this coupled system of n atoms. And for clarity, we restrict our treatment for now to a one-dimensional chain of atoms, because, well, first of all, we will learn a lot by just considering a one-dimensional case. And we do not need to deal with vectors. We can really deal with scalars. And this simplifies understanding of situation a great deal. And later on, don't worry, we will generalize our approach to three-dimensional case. So this we will do in the kind of final lecture in 4.1. And this is where you might have trouble in this final lecture when we are generalizing things. So please be patient and be rigorous in the first parts. So we will start by considering a monoatomic lattice, and this is essentially what we want to solve first. And we want to solve what kind of oscillations may take place in such lattice. And we are now, remember, we are considering atomic lattice oscillations. We are not considering movement of electrons. So we consider the atoms, and like one atom is labeled with S, and we now let that couple with the adjacent atoms. And these we label S-1 and S+2 as we show in the figure. And the separation between the atoms is A. A is the lattice constant, and this is true when the system is in equilibrium situation. So in equilibrium, essentially all the displacements we have for each of these atoms US will be 0. So that's the starting point. And now we start wiggling the atomic lattice, and then we start seeing what kind of oscillations may take place in it. And again, we will assume that harmonic approximation holds. So we do not consider anharmonic contributions, but I must warn you that if we would perturb the system quite a bit, then we would also take into account these kind of contributions. And there are plenty of occasions of physics where this approximation is not valid anymore. So for example, when these lattice vibrations are interacting with each other, so for example, a phonon, a lattice vibration, a quasi-particle may seem to be hitting another phonon, and it maybe seem to be scattering, and these kind of events, for example, they are nonlinear processes, and we need to actually go beyond the harmonic approximation to understand what happens. Superconductivity is another example where we see that something actually happens, that somehow electrons are being coupled via phonons to each other, and so those are some examples. Or Raman scattering as a process, which also happens in solids, so that these are some example cases. Not always. Harmonic approximation is good approximation to make, but here we just assume that it's okay. And now where things become different compared to the earlier treatment is that now we have a restoring force, and I denote that with Fs. That is then proportional. We assume it to be proportional to the differences of the displacements. So essentially the restoring force is assumed to be a form that Fs is equal to gamma, the spring constant, the coupling constant, times us plus 1 minus us. So the difference of displacements with respect to the s and s plus 1 atom, and then plus another contribution of us minus 1 minus the us. So this is essentially the restoring force our est atom feels. And now we will write an equation of motion for this est atom in question. And this is essentially following from the laws of Newton. So we just write F equals ma into the situation and solve this kind of system. So we write an equation of motion, and we have the mass of our atom still m, and we have the second time derivative of our displacement us. And then on the other side, we now have the restoring force. So gamma times us plus 1 plus us minus 1 minus us. And this can be solved by trial solution. So we just assume that our displacement us is proportional to exponent minus I omega t, where omega is the angular frequency of the oscillation. So what we get is that we have this form for the equation as we saw, and now we just put in our trial solution and calculate what is the second time derivative, and this is what we get. So we have minus m times omega squared times us. And then we do nothing for the right hand side, so that just remains intact. And this equation, it may not look familiar to you or solvable, but actually it is quite solvable. So it's essentially a linear difference equation, and it has a solution of form us plus 1 or minus 1, and this is of the form that we have u, the displacement times exponent iska times exponent plus minus ika. So essentially we seem to have contributions depending on the kind of displacement. Like are we on the plus 1 direction or the minus direction? And this we can now place, we assume that the solution is of this form, and we can now plug this into our equation, and we can solve the above difference equation. So we just plug in these guys into here, and we can then see what we will get out. And that can be solved, the system, and the requirement that we will find after we do the algebra is that our solution must comply with this equation. So the angular frequency omega squared must be equal to 2 times gamma divided by m times 1 minus cosine of Ka, where K is the wave vector of our lattice vibration. And please note, K, of course, it looks like a scalar, but because when we generalize our treatment, K becomes a proper vector, so it becomes a vectorial quantity, then we really are dealing with a vector here. And that's why I try to use terminology that makes it obvious that which of the quantities turn into vectors when we are generalizing to a three-dimensional solid. And this equation is known as the dispersion relation of our system. And these dispersion relations, they are very important in solid-state physics and physics in general. This concept is really present everywhere, so it's ubiquitous. And what physically, when we look at the mathematics, what the dispersion relation tells to us, well, in a nutshell, it relates the frequency omega with the wave vector k, as you can see from the equation. But this is actually quite nice because this is the kind of cornerstone upon which we are building when we want to understand, for example, the thermal conductivity of solids and heat capacities of solids, as we will learn later. So this dispersion relation mathematically just tells us that what is the omega as a function of k wave vector. Simple as that. But of course, it seems abstract, but once we start using it, we start realizing it that the dispersion relation is actually very important to understand the response of our system. So form of the dispersion relation, omega k, that is proportional to omega and not the square, as we saw, is actually preferred in treatment, and that's why we are using the de Moivre's formula. If you have taken the optics course, please remember that the de Moivre's formula can be easily derived when we just recall the polar notation of cosines and sines, so the Euler's notation. We can very easily derive Moivre's formula, and when we do that, we can simplify our equation to be a form that is linear with respect to the angular frequency omega. So omega squared times omega squared equals 4 times gamma divided by m times sine squared times 1/2 times Ka. And this is now we can easily take the square root of this and we will get the form that we were looking for. So omega as a function of k, and then we have the square root of 4 times gamma divided by m, and gamma was the spring constant. And then we have the modulus of sine times Ka times 1/2. So this is the formula we have for the dispersion relation. And this is our final form for now, and next we will start dealing with its implications, so what this actually means in practice. So let's start by just plotting this dispersion that we got in a range where k, the wave vector, ranges from -π/2 to 2π/2, over a. And in fact, it's enough to just consider a range that is slightly shorter, but hopefully this choice of plotting helps you out to understand what the periodicity of the structure implies to us and for the solutions. So in fact, it's just enough to consider the range from -π/2 over a to π/a. And this area is known as the first Brillouin zone. And this I will confuse you maybe with the terminology, but this first Brillouin zone, we are now actually in the so-called reciprocal space, and this Brillouin zone is in fact the Wigner-Seitz cell of our system, but in the reciprocal space. So here would be our lattice point in the reciprocal space, in the origo of this treatment. So but more of this when we generalize to the three-dimensional case. And in this case, we really see that the Brillouin zone is actually a volume, and there we will speak a little bit about the Wigner-Seitz cell fact of it, or the nature of Brillouin zone being a Wigner-Seitz cell, and so forth. So we are plotting here in the blue the dispersion relation, and this is how it looks like. And we can see that there's a sharp point due to the fact that we had to took the modulus of the sine. And since I was plotting here, we see that in fact we are starting to repeat the curve, how it looks like in here when we go from π/a to 2π/a, and it looks exactly the same as in here. So mathematically, it's just enough that we consider what happens in here in the gray area, and this we call first Brillouin zone. And we do not need to really go into these other parts. Sometimes we do have scattering processes where we should really go to these other Brillouin zones, and then sometimes they do need to be taken into account, but we don't really go there in this introduction course. But if you're really curious, I recommend that you start reading in detail Kittle's book, and there, once you just go far enough, you start seeing that also the other Brillouin zones actually matter, and where they start mattering. But we do not go there, so let's just be happy of that fact. And now let's consider two limiting cases so that we can see also their usefulness in later on. Let's first consider a case where the wave vector k is roughly 0. And since when k is roughly the 0, we see that we are dealing with the region that is close to the lattice point. So we're dealing with the omega. Sorry, not omega, but the 0 point here. And in this case, the sine 1 over 2 times Ka is roughly, because K is small, it's roughly 1 over 2 times Ka. And with this, like the dispersion frequency, dispersion relation, the angular frequency turns into gamma over m, square root of that, times Ka. And this is the velocity of our wave times the wave vector. And please recall v, the velocity equals to omega per k, applies for waves, and here velocity v is actually the velocity of the sound waves. So we see here that when you're in this region, this applies, and this relation works out, so that the velocity of these waves, these oscillations of atoms in the periodic structure, these oscillations seem to be propagating at the speed of sound in a material, and this is what happens. Then the other case is that we are then dealing with the edge of the Brillouin zone, and in this case the k value is either plus minus pi over a. And then let's look what the mathematics implies in this case. And now, like the k is not close to 0, but it's actually 2 pi over lambda. And that's the usual general relation for a wave vector, or the amplitude of the wave vector. And from this, we can derive what is the lambda, what is the wave length of our atomic oscillation, and that's of course 2 pi over k. And this is then approximately 2 pi a divided by pi when we plug in the k shown in red into the equation, and then we get that the wavelength is roughly 2 times a, where a is the lattice constant. So we see that that's roughly the wavelength that we're dealing with here. Group velocity of our wave, if we would calculate it, Vg, that's defined as the partial derivative of angular frequency omega with respect to k. And in this case, that's roughly a 0. And this implies to us that we actually, in fact, here we have a standing wave here when we are looking at the slope of our wave. So in this case, the oscillation doesn't seem to be moving around. Rather, it seems to be frozen out and forming a standing wave. So if you would look into these two limiting cases and what they imply graphically to us, what kind of oscillations we're dealing with, I'm showing that in this figure from the booklet. And here, let me just firstly go reminding you that we are really seeing here oscillations of atoms. So we're not looking at electrons here at all in this chapter, essentially. We're just interested in the oscillation of atoms. And we are now interested in these oscillations with respect to their equilibrium positions. This is what we are interested here. And we do not consider movement of electrons. And here, the first type, when we had k far smaller than pi over a, so roughly k close to 0, then the wavelength is very large compared to the lattice constant, and then we have in-phase oscillations. So the different atoms, they are oscillating in the same phase, and this is roughly how it looks like, the oscillation. And then when we are at the edge of the Brillouin zone, so when k equals to plus minus pi over a, then the wavelength is 2 times lattice constant. And then when we are looking at the different regions, we actually end up with oscillations where the adjacent atoms, they are out of phase. So they are kind of wobbling around with different phases in here. And this is quite different type of an oscillation than the in-phase oscillation we're dealing with when we are close to the 0 of the Brillouin zone, close to the so-called gamma point of the Brillouin zone. But more of that later when we go to the 3D case. Okay, So what we have here is that in the two-dimensional case, these lattice vibrations that we have found out, they would look like below. So we may either have longitudinal oscillations, and these then subsequently, the vibrations we have are called longitudinal lattice vibrations, where the atoms are moving in this direction. and these kind of displacements is then what we are dealing with. But that need not be the case only, so that we can only also have waves that are oscillating transversely with respect to the propagation direction, and this is what is being highlighted here. So we can also have transverse lattice vibrations when the nearby atoms are now oscillating along different directions. And since we're dealing with the three-dimensional solid, we may have two different orthogonal transverse directions. So like we may have atoms displacing along this direction, or then like out of the plane of this slide. So like if you would have a propagating wave along z direction, then the atoms could also oscillate either along x direction or y direction. And in the longitudinal case, when the wave is moving along z direction, the atoms are also oscillating along that z direction. And please distinguish that these possibilities, they are quite different of the possibilities of, for example, how electromagnetic wave oscillates. Electromagnetic wave is a transverse oscillation, so we do not have this kind of longitudinal oscillations when we are dealing with light and its oscillation. So, the periodicity of the dispersion relation, omega k, was found to be 2 pi over a, and this we can really see from the figure that that's the region we only need to consider. And it's just enough to describe the dispersion relation in this first Brillouin zone. And this is a very, very important concept, because the mathematics that we use to understand physics in periodic structures, then when we are describing these mathematics in a reciprocal space, then it's enough to be in the first Brillouin zone most of the time. And it is not a coincidence that this periodicity corresponds to the amplitude of the reciprocal lattice vector B, and that was defined to be 2 pi over a. And this arises from the fact that what we are showing here, this is actually the reciprocal space description of our wave. So in a way, like we haven't told you, but essentially we have taken a Fourier transform out of our oscillations. And now we are looking at the different frequencies of oscillations. And if you would want to know like how the atoms oscillate with respect to time, we would take the inverse Fourier transformation, and then we would actually be able to describe how the atoms seem to be oscillating in real space. So in the real three-dimensional solid. And this Brillouin zone is a very key concept in solid state physics. So please try to memorize it, what it is, and try to understand what it is. And since this reciprocal lattice vector is B 2 pi over a, there's really just a single reciprocal lattice point that fits inside this first Brillouin zone. And it's in the center of the Brillouin zone, so in fact, this first Brillouin zone is the Wigner-Seitz cell of the reciprocal lattice. So that's how terminology actually goes. So here is our lattice point, and it's exactly in the middle of our reciprocal lattice. Exactly in the middle of the Brillouin zone is our lattice point, and that's it. And when we generalize to three-dimensional case, the Brillouin zone becomes a volume, but even in that case, we know that it's the Wigner-Seitz cell in the reciprocal space, so the lattice point is in the center of this volume. That's how things generalize when we go to three-dimensional case. So this is that. We have now covered the monatomic lattice, and I think we do have time to go forward to the diatomic lattice case. So let's now extend our treatment, and we are still considering a one-dimensional infinite lattice. So we are still thinking that we have an infinite amount of atoms, and they form a one-dimensional lattice. But now what we do is that in each of lattice points we actually have two atoms. So essentially the terminology goes that we are dealing with a diatomic lattice here. And again, we let the atoms to be coupled to each other by springs or essentially by like electrostatic forces and Pauli repulsion. But the physics will be the same in the end. The mathematics will be the same. So please have a look at the figure and what is the difference between the earlier monatomic case. So now, instead of identical red spheres, we are now considering red spheres and differently sized blue spheres. And also we have different masses because, as we know, with the different atoms, we may have different masses. And then we are wanting to understand how this system then can wiggle around. The lattice constant is still A, and the atomic displacements from their equilibria positions are denoted with US and VS for the S atoms, or actually more precisely, kind of like different atoms in a single lattice point. And now what we have is that we can write the equations of motion, and essentially it's the same kind of mathematics as earlier, but slightly more complicated because we do have two different atoms there. So we can write the equation of motion for the first atom. So that will be m times the second time derivative of US. And this is the dot notation looking like this. And then we have the same kind of forces, restoring forces as earlier. But now we have a contributions from the nearby different atoms. So we have actually now like the restoring forces. We again here, I'm not saying it anymore, but we are assuming again that it's only the difference between the different displacements that matter, and that's why we get this distances here. So you can like do the math yourself. You can consider the S particle, and then you can calculate like what is the restoring force to the nearby S-1 blue atom, and then to this other S+1 blue atom here. The nearby atoms, like this is in the same lattice point in the same unit cell. So this is the VS atom or its displacement, and here we have the VS-1. So this is the nearby different looking atom from the adjacent lattice point. And then we write the second equation for motion for the other particle, and we have this kind of equation here. So essentially, like this is the same math as we dealt with in the monoatomic case, but now we are just dealing with two atoms. and what is the difference here is that now actually we have coupled linear differential equations. So they are still linear. The oscillations that we have are still linear, but they are coupled. So as we can see, we are looking at the displacement of US, and we see that also depends on the displacements of the atom V, the different atoms displacements, so VS-1 and VS. And similarly, when we are looking at the displacement of the S different looking atom, so we are looking at the displacement VS and its oscillations, we see that that's also depending on the US and US+1. So these equations are in fact coupled with each other. But this is nice. Like it's not that hard to solve, and this actually like provides us a nice piece of mathematics and elegant physics. So we use the trial solutions that are of the form, and this is very familiar. So that US displacement is a form where we have an amplitude of the oscillation U times exponent I Kas minus omega t. And then we have the other solution, trial solution for the other particle, and that will be the displacement Vs, and that's equal to V, the amplitude of the oscillation, times exponent IKAS minus omega t. So these are the trial solutions that we will then place into our coupled linear differential equations, and we will then solve what the equations motion will look like. So we will now have coupled equations, and because they are still the trial solutions of simple harmonic oscillations, we can readily calculate the time derivatives, and this is what we will have with what will follow. So we will have minus omega squared times m1 times u times gamma times v plus times 1 plus exponent minus IKA, and then we have minus 2 times gamma times u. And then the second equation, we similarly get minus omega squared out by just performing the second time derivative calculation times m2 times v, and that must be equal to gamma times u times exponent IKA plus 1, and then minus 2 times gamma v term. And this is coupled equations, so the u's and v's are mixed, and we must solve this. So I don't repeat myself, these are the two equations we found out. And we will now just basically transform these equations into a matrix equation. And this is the nice thing about the fact that we are dealing with a linear system of equations, so that we can actually really write it into a matrix equation that will be a form that on the right and left-hand side we have zeros, and then on the other side we have 2 times gamma minus omega squared times m, then we have these other terms. So it's really a matrix, and then we are multiplying with a vector uv. So this is into what kind of form we can solve by just moving these terms into the other side, and then transforming this coupled equation into a matrix equation. And a matrix equation like this has a unique solution when the determinant of the coefficient matrix vanishes. And this one matrix we can see here, that's called a coefficient matrix. And when the determinant of that matrix vanishes, we will have a unique solution. And that's what we're seeking here. So we can calculate the determinant of the coefficient matrix, and I do not do the calculation here, but Kittel tells that it's long but straightforward calculation, and the end solution will be that we have a dispersion relation that is of a form that we have omega squared times gamma times 1 over m1 plus 1 over m2, and this is the first term, and then we have plus minus gamma times 1 over m1 plus 1 over m2 squared minus 4 times m1 times m2 times sine squared ka divided by 2. And this is in the square root, inside a square root. So this is our new dispersion relation for a diatomic lattice. It's still a one-dimensional lattice, but nevertheless, like, it's diatomic. And we will now look into the kind of subsequent changes that we have in our dispersion relation, because of the fact that we also have those second atoms that look different in our inner lattice. And this is now the plot of our dispersion relation. I'm still plotting this similarly with the omega versus k. So I'm not plotting omega squared here, so that I'm just using the normal convention. And what we see here is that now we actually have two different branches. So we have plus branch and minus branch. And the other branch behaves as earlier. This is our familiar looking dispersion relation. But the other branch now actually looks quite different. And this is the other solutions that we now see are emerging due to the fact that we have two atoms in our lattice. So what we see is that this acoustic branch, and we will learn later why we call them acoustic and optical, but acoustic branch behaves exactly as the branch we found out for a monoatomic lattice. And this where when the K goes to 0, the omega goes to 0, and this is the kind of behavior that we have here. So we still have this behavior there, and this we will use later when we are calculating the heat capacities using the Debye model. So please be warned that we will come to this later. And then this optical branch is new and different, and why this is so, and why this is actually behaving quite different from the acoustic branch is that we can actually excite lattice vibrations that are residing in the optical branch via photons. Momentum of a photon is quite small, so please recall that the momentum of a photon is of the form that we have reduced Planck constant h bar times k, and this is of the order of like h by lambda. And this is actually quite small of a value of a momentum. But phonon momentum near now matches the momentum of a photon when we are in the k close to 0 point. So that when we are in this location, our k, and this is what we are seeing at the x-axis, like what is the amplitude of our wave vector. And when we are here in this location, looking at here, we see that our wave vector is 0. And since the momentum of our photon is also small, we can actually have a system raised into a state residing in here by shining light, or at least electromagnetic radiation, into the system. And this is why this branch is called an optical branch, because we can actually optically excite atomic vibrations that reside here. Of course, the frequencies are such that we don't really use optical light, like visible light, but nevertheless, like we can use electromagnetic radiation. And phonon dispersion that we see, it flattens out near the k equals 0 or k close to 0 region. And here again, we see that we have standing wave solutions, so that we can imagine that in this location when we are here, we actually have two waves, other propagating in a different direction and the two other propagating in different direction, and then we actually have a standing wave formed here. And what this implies for the upcoming sections is that these phonons don't really transfer energy as such. Standing wave does not transfer energy. We need a propagating wave to transfer energy. So this is the kind of take-home message when we are looking at the optical branch. So we are now at the end of our lecture. Thank you for joining me and listening for me until the very end. So we have seen that when we are dealing with a one-dimensional lattice, and we're still dealing with a infinitely long lattice of atoms, we are looking at the solutions, what kind of vibrations we will have on it. And these vibrations are important because these are the vibrations that can store energy. And these are the vibrations that can transfer energy. So these are the quantities of interest when we are looking, we want to understand what is the heat capacity of a solid, or we want to understand what is the thermal conductivity of solid. So it's really these guys, these atomic vibrations that make all of that happen. So we may have either an acoustic branch when we are looking at these lattice vibrations, and this is how it looks like in the first Brillouin zone. And then when we also have a second atom in our basis of lattice, we may also have an optical branch. And the optical branch, the name comes from the fact that we can actually excite these kind of lattice vibrations by shining electromagnetic radiation into the matter. And this acoustic branch, it's called acoustic because we do not excite it using electromagnetic radiation, and rather these vibrations here, they correspond to sound vibrations in matter. So if we would want to excite these lattice vibrations, we should actually put a speaker, a low frequency speaker, next to the piece of a solid, and we should blast away, and then it would be this acoustic sound that would actually make this piece of a solid to oscillate and have these acoustic vibrations. So this is what I wanted to say in this lecture. I thank you, and please join me in the upcoming lecture when we are now breaking apart this assumption we make of having an infinite chain of lattices, and then we will go into a finite chain of atoms, and we will see what we will learn by making this transition in our size of a lattice. So thank you, and bye bye.